Welcome to Spotlight on Tutoring Science with SP Tutors. My name is Chris and I'm Head of Chemistry at Notre High School, Norwich, an EEF research school. I'm delighted to be joining SP Tutors in Spotlight on Science with the aim of achieving their vision of accelerating progress for children's learning, especially those most disadvantaged during the COVID-19 lockdown, through high-quality, evidence-informed tutoring. In this Spotlight on Science, we'll be looking at strategies we can use to aid the teaching of reacting mass calculations within a typical chemistry syllabus. Let's start by taking a look at how our students might be asked to use a reacting mass calculation and the underpinning skills and knowledge needed to tackle such a problem. Reacting mass calculations are used to make predictions about the mass of product or products that will be made within a chemical reaction, or the mass of reactants that might be needed to produce such a desired mass of product. Before attempting reacting mass calculations, students should be confident with the following key skills and ideas: balancing chemical equations, calculating relative formula mass, MR, interconverting between mass, moles, and relative formula mass, and finally applying ratios. Let's take a look at an example question so that we can see how we might structure our working in a clear format that can then be applied to answer subsequent problems. So here's our example question. What mass of iron, Fe, is produced when 224 grams of iron oxide, Fe2O3, reacts with an excess of carbon monoxide? Before we get stuck into the question, it's probably worth having a look at with students some of the key terminology that's being used here. In particular, this term here, excess. Now, the idea of an excess can be quite challenging for students to understand. We might like to liken it to some kind of analogy such as baking, where the reactants in our chemical equation are much like the ingredients and the products are much like the thing we're trying to make, for example, cake. And we might say that if we were to have a limited supply of one of the reactants or one of the ingredients and a large amount of the other ingredient, that we would still be limited in terms of the amount of cake that we could bake because we needed all of the ingredients, not just some of them. So when we talk about an excess, we might want to talk in terms of having more of that ingredient that we need and the other one limiting how much we can make. This is going to help students when we start talking about limiting reagents in subsequent calculations. So let's have a look through the calculation that we're going to perform then and how we can set it out. Let's start with how we can arrange this for students to better understand. One of the key things I like to do is I like to set it out in a clear table format where we have mass, molecular weight, and number of moles clearly laid out so that students can identify which piece of data relates to which quantity in the equation. So we start our process here by writing in all of the data that we know. So our question has told us that we have 224 grams of iron oxide. So here's our iron oxide, and we can write in that data into the table 224 grams. And it's asked us to find out what mass of iron, Fe, we produce. So it's worth at this stage marking where we're trying to find our answer, just so we can keep sight of which bit it is we're working towards. The next thing we need to do is we need to then start identifying the molecular weights of the parts of the equation that are relevant. Now at this stage, students might start trying to calculate molecular weights for all the components in the equation. It's worth just emphasising that they only need to calculate the relative formula masses for the individual components that are of interest. So for our iron oxide here, that's 160 grams per mole, and for our iron here, that's 56 grams per mole. Note, the values that students will likely be using at GCSE will be rounded values of their periodic tables that don't typically involve decimal places. Only a few of the elements on the periodic table carry a decimal place at GCSE. As part of students' works looking at moles, they should be able to now convert between mass and relative formula mass. This relationship can be rather usefully summarised in this form. At the top we have mass, we have relative formula mass, and we have number of moles. And we can see that if we put into our equation the 224 grams of iron oxide and we have a molecular weight relative formula mass of 160, we have a number of moles of 1.4. And we can pop that into our table so that we can keep track of our data. At this stage, we now need to use the relationship of moles from our equation using the stoichiometry. So if we look at our equation, we should then be able to identify the number of moles for each component of the equation. So for the iron oxide, we have 1 mole, And it's worth pointing out to students that the absence of a number over here does not indicate that there are no moles of it, only that there's one. Much in the same way as within maths, we might represent 1x as just writing x. We have 3 moles of carbon monoxide, we have 2 moles of iron, and we have 3 moles of carbon dioxide. And the important parts within that ratio are the number of moles of the iron oxide to the iron, which is a ratio of 2 to 1. So we can draw an arrow coming across our equation and indicating on that arrow the relationship between those two. So that's a 1 to 2 ratio. And students will then need to apply that 1 to 2 ratio to calculate the number of moles of iron that we have. So 1 to 2, or 1.4 to 2.8. And we can then use the same relationship of mass, molecular weight, and number of moles as we've used before. Mass, molecular weight, number of moles, and again we can input our data. So this time our MR, our relative formula mass, is 56. Our number of moles is 2.8. And from that equation we can calculate a mass of 156.8 grams. We can write that in our table, 156.8 grams. It's worth noting when students are asked to calculate relative formula masses, we might find that because the equation shows 2 moles of iron being generated, some students might calculate twice the relative atomic mass of iron, at which point we just need to be careful to emphasize this idea that relative atomic masses and relative formula masses are not dependent on the number of moles of them within that chemical equation. Next steps for our students might involve calculating the mass of reactants needed to produce a desired quantity of product, or determining the relative formula mass of a reactant or a product from mass data. It could also be used to identify a limiting reagent and an excess reagent in a chemical reaction. Students may be studying titration and may look at concentration and volume quantities using a similar structure.